Hello, I'm Mr. McBrien. This is SPH3U, Mechanical Work and Power. So the Ontario curriculum contains the ideas of explaining energy, work, and power, describing the conditions required for work to be done, and solving problems related to work, force, and displacement along the line of force. That's what we're going to be considering today. So our objectives. We're going to define work and energy, some things that are actually kind of challenging to define. We're going to learn some conditions that have to be met so that work can be defined to be done. We'll learn how to calculate the work that's done. We'll define power and learn how to calculate power as well. So, mechanical work. We can define mechanical work on an object as the amount of mechanical energy that is transferred to that object by a force, like this pitcher's doing to the baseball, transferring his potential energy in his body to the baseball to accelerate it. And so work, we can have a pretty simple starting point definition that work is just the change in the energy. So what's energy? Well, mechanical energy associated with an object is the part of its total energy which is subject to change by mechanical work. And of course, this is a somewhat redundant definition, but it leads us to kind of a challenge that we have. Energy is kind of a fundamental concept in physics, and it's kind of hard to define it in terms of anything more fundamental than itself. But we'll take a stab at it today, and I think from a two-pronged approach we can get a pretty good understanding of what energy means. So we're going to consider kinetic and potential energies of an object and hope to understand mechanical energy in that context. Okay, so kinetic energy, we all have a pretty good feel for that. Kinetic energy is the energy associated with motion. If something is moving, it has kinetic energy. If it's moving fast, it has more kinetic energy. Potential energy, on the other hand, is energy we associate with something that could be used to do something else. And we'll be talking more about potential energy this week. Okay, another example of energy, thermal energy. Thermal energy associated with the temperature of something is energy within the particles of a substance, of course. We often talk about kinetic energy as, thermal energy as being a kind of kinetic energy. We think about things like gas particles being accelerated up to move faster when they're heated. And that's true. A component of thermal energy is kinetic energy, but some of it's actually potential energy as well. That's just a little more subtle to understand. So the kinetic energy is in the movement of the atoms. The potential energy is contained in the deformation of the bonds in that object. So we can almost think of it as stretching a spring or an elastic band. And so that we think of as potential energy. Okay, a little bit about energy units. Modern science, we tend to want to define the units of virtually anything in terms of a few fundamental numbers, and energy is no different. So we have the joule for energy, and the joule is actually 1 joule is equal to 1 kilogram meter squared per second squared. And as you know, I like to relate that back to the fundamental equations that we use to calculate these things, and we'll be doing that. most of us look at that number or that equation, 1 kilogram meter squared per second squared, and have a tough time rationalizing that. We'll actually come back to it and rationalize it a bit, but we're also going to look at some other units that may be a little more descriptive about energy. Okay, so other units that we have, if we want to describe very small amounts of energy, it's more convenient to use a smaller scale. And 1 erg is, instead of kilograms, we have grams. Instead of meters, we have centimeters. And this drops our size of our unit by 7 orders of magnitude to give us 1 erg equals 1 times 10 to the negative 7 joules. If we want to talk about large amounts of energy, we can use kilowatt hours, and kilowatt hours, 1 kilowatt hour is 3.6 times 10 to the 6 joules. And a calorie is kind of interesting. So maybe that's the most familiar energy unit for us at this point, and it's 4.184 joules, typically used to describe the energy in foods, of course. But the calorie is actually its own unit and is worth discussing for a few seconds. So it has its own definition instead of being in terms of other fundamental units. A calorie is the amount of heat required to raise the temperature of a gram of water by 1 degree Celsius at a pressure of 1 atmosphere. So this can give us a little more insight to what energy is, right? What it can be used for. It can be used to, for example, heat up water. And when they originally designed the calorie, it was on that basis that they did so. Typically, we use calories with a large C when we're talking about food, which are really kilocalories. So that can get a little confusing. Again, bless our SI units for not being quite so arbitrary. But anyway, it's pretty simple. Kilo meaning 1,000, so 1 calorie with a capital C is just 1,000 calories with a small c. And of course, instead of being 4.184 joules, it's 4.184 times 10 to the 3 joules. Okay, back to work. So we can talk about work then. The simplest case of calculating work. We can say if an object is moving in a direction and we apply a constant force parallel to that direction, we can define work as work equals force times the distance over which that force was applied. And that's a pretty simple calculation. We've already talked about force in this course. Delta D, we know all about this. So it's really a pretty simple way to calculate the work done. Now, one thing to keep in mind, that work is a scalar quantity. Okay, so let's look at the first example. So we apply a horizontal force of magnitude 40 newtons to push a 10 kilogram box 15 meters across a frictionless surface. We sure love our frictionless surfaces in this course. So we want to find the work done in the box. Really pretty straightforward. So our Gus is force equals 40 newtons. The distance is 15 meters. And the work is equal to force times change in distance, or 40 newtons times 15 meters, or 600 joules. Now what's fun here is we were given the mass of the box, but it was irrelevant. The work done was only in terms of the distance traveled and the force applied. So the mass does influence the acceleration that resulted from our work, but it doesn't affect the work itself. Okay, example 2. In this example, we apply a vertical force of 40 newtons on the 10 kilogram box as it slides 15 meters across the frictionless surface. And the question is, what's the work done on the box? So all the numbers are the same. The force is 40 newtons, the mass is 10 kilograms, and the box slides 15 meters across the frictionless surface. So what's the work done? Well, it should be the same, right? Actually, no, it's not. So, in this case, our work is 0 joules. And this might seem kind of confusing at first, but we can rationalize why this is the case. So if we go back to our definition of work, the mechanical work on an object is the amount of mechanical energy transferred to that object by a force. When we apply the force at 90 degrees to the direction of motion, no energy is transferred. The box doesn't accelerate, it doesn't decelerate, no work is done. And that's a very important concept, and we have to really get our heads around that in this course. So in our case, when we're pushing vertically on the box doesn't accelerate. Its mechanical energy is constant, and the force applied doesn't count towards the work. So if we want to create a more complete definition of work, we can do so if we think about the angle at which the force is applied, theta, and the distance the object moves. And we can insert a cos theta term associated with that angle. So what does this do for us? The only portion of the force that counts towards the work done is that component of the force in the direction of the motion. Work equals force times cos theta times the distance traveled. So, our next example. We apply a force of magnitude 40 newtons at a 60-degree angle with horizontal to push the 10 kilogram box 15 meters across the frictionless surface. So it's the exact same magnitude of all the values, except it's at a 60-degree angle. So we have one more term now. Our force is 40 newtons, our distance traveled is 15 meters, our angle is 60 degrees, work equals F times cos theta times the distance equals 300 joules. And notice that that's 1/2 of the value from before. Why the difference? So the answer is that half of that force was dedicated to lifting the object instead of moving it or accelerating it. And working against gravity can't reduce the friction because the friction was already 0. So it's just wasted effort. Okay, so I invite you to pause the movie for a second and think about this concept. Can friction do work? Please pause the movie and think it over and come back and we'll talk about it. Okay, welcome back. After you thought about it, maybe you came up with this concept. Since the friction opposes the motion, it'll actually do negative work on the object. It'll reduce its total mechanical energy. So let's see how this works in practice. Let's say we apply a horizontal force of magnitude 40 newtons to push a 10 kilogram box 15 meters across the surface. But the frictional force is 10 newtons, and we want to find the work done by friction on the box. Well, we can set it up the exact same way. The force is 10 newtons from the friction. Our distance again is 15 meters. But here is the key thing. We introduce a theta of 180 degrees. In other words, the friction is opposing the motion. Now we can calculate the work in the exact same way. Work equals F cos theta times distance. Substitute in, and a cos 180 degrees is equal to -1, And so this gives us negative 150 joules. So now what we can do is consider the total change in energy of the box. We can consider the work applied by Ms. Roseberry and the work done by friction, and do a simple algebraic sum. And we can see 600 plus negative 150 equals 450 joules of work done on the box as a net. And of course, where did the energy, the work done by friction, where did it go? Well, according to the law of conservation of energy, it has to go somewhere. It creates heat and it creates noise. Okay, so let's start a quick discussion on the concept of power. Power is the rate at which work is performed or energy is transferred. So, anytime we hear rate, we think divide by delta T. This is no exception. Power is the work done over an interval, over delta T. And this gives us our equation for so that we can calculate power. So, of course, since work has units of joules, time has units of seconds, we can have units of joules per second or watts. So, today, we learned the definitions of work and power. We learned how to calculate work done. We learned how to consider the idea of force applied at an angle in order to calculate the work done by that force. And we considered the special case of the effect of friction on work. And then we learned how to calculate power. For practice, please read section 5.1 in the textbook, pages 222 to 229, and do the practice problems specified on the screen. Thanks for listening.